Math 2414, Series Video 2, Partial Sums and Convergence of a Series. Well, let's get right into it. On the screen you see an infinite series. It's the sum of 1/2 to the nth power as n goes from 1 to infinity. Now, before we get into this problem, I want to introduce a little bit of vocabulary. The variable used in the limits of a sum is called the index. The value that the index begins at is called the lower limit. Lower limit. The value that the series ends at is called the upper limit. No surprise there. And the expression that you're taking the sum of is called the argument. That's what I call it. So throughout the rest of these videos, I will be referring to the index, the lower limit, the upper limit, and the argument. All right, so how do we even begin to discuss how does an infinite sum converge? Because technically speaking, it never stops. Well, let's start by writing out a few of these terms and talk about the idea of something called partial sums. If we were to write out this sum, we would start by letting the index equal the lower limit in the argument. So we would have 1/2 to the first power plus, and then we would just let the index go to the next whole number, which would be 2. Put 2 in for the index in the argument. Get 1/2 squared, then plus 1/2 cubed, plus 1/2 to the fourth, and so on. Since this is an infinite series, it will not stop. It will go forever. So in theory, we can't actually add an infinite number of things. So what do we do if I fix this 3? Well, in order to examine if an infinite series will converge, we have to first look at what are called partial sums. Hiding this text box. For an infinite series, or even finite, nth partial sum, written, say, capital S. And I'm gonna draw a subscripted n in just a minute. Is the sum when the upper limit is n. In other words, we stop the series. Now, I'm kind of painting myself into a little corner here that I'm about to fix, because when I talk about the nth partial sum, and I didn't leave space after the S, got to write the subscript. Give me 1 second. Okay. There. When we talk about the, well, it's supposed to look like this. Not a very good job of it. But when we talk about the nth partial sum, we're basically saying that we stop the series at a certain amount. The corner that I painted myself into is that I've already used the letter n to represent the index. So why don't we go change that n to something else? The actual letter that the index is completely irrelevant. You can use any letter you want. Gee, what letter should I use for index? How about I? It doesn't change a thing. It doesn't change how you expand the sum. It's still 1/2 to the first plus 1/2 to the second, and so on. But if I'm going to use n to represent an upper limit, then I can't also let it represent the index. So in other words, what I'm saying is that the nth partial sum is the sum from I equals wherever it starts, and we'll just say it starts at 1, but keep in mind that the lower limit can be any number, to n from ai, whatever your sequence is. So in other words, the nth partial sum is what we get when we add the first n terms. So we're going to take some partial sums of the series that we're currently looking at on the next page. So let's start with the first partial sum. This is going to be pretty easy. First partial sum is the sum we get when we add up one term. Well, that's just the first term. Well, 1/2 to the first power is 1/2, so not a whole lot to look at there. Second partial sum is the sum we get when we add up the first two terms. So 1/2 to the first plus 1/2 to the second. That's 1/2 plus 1/4, 3/4. If we wanted to do the third partial sum, we would add up the first three terms, 1/2 to the first plus 1/2 to the second plus 1/2 to the third. That would be 1/2 plus 1/4 plus 1/8, 7/8. Just for kicks, let's go ahead and do the fourth partial sum, which would be 1/2 to the first plus 1/2 to the second plus 1/2 to the third plus 1/2 to the fourth. 1/2 to the fourth, which would be 1/2 plus 1/4 plus 1/8 plus 1/16. If you get a common denominator and add, you get 15/16. So those would be the first four partial sums for the infinite series that we started on this page, where we had the sum from I equals 1 to infinity of 1/2 to the I power. So what does this have to do with the infinite sum? Well, here's what it has to do with it. Let's widen this text box. An infinite series is said to converge to, we'll say capital S without a subscript, if the sequence of its partial sums converges. This is more of a definition than anything. The way we're going to add up an infinite series is we're going to take partial sums, so first term, some of the first two terms, some of the first threes, first four, first five, et cetera, and look at those sums as a sequence and see what they're converging to. So going back to the series that we started with, sum from I equals 1 to infinity of 1/2 to the I power. If we look at the sequence of partial sums, so we're looking at the answers to the first four partial sums that we had before, which are back over here, and I'm going to circle in red. They were 1/2, 3/4, 7/8, 15/16. 1/2, 3/4, 7/8, 15/16. Can you predict the next one? There's all kind of patterns going on here. The denominators are forming a geometric sequence because the ratio of consecutive terms is the same. Translation, I'm multiplying by the same number each time to move the denominators up, so that would be 32. What about the numerator? 1, 3, 7, 15. There's a few ways to look at it, but if you're paying attention, you'll notice that each numerator is just one less than its corresponding denominator. So we are getting this sequence of partial sums, and the question that we need to ask is, what does this converge to? What does this sequence converge to? And if it converges to something, then that will be our infinite sum. Well, if we want to find what the sequence converges to, it would help if we had a closed form, a function, that told us what the nth partial sum is. And I think we can come up with one if we can deconstruct these partial sums. So let's do that. So what do I mean by deconstruct? You'll see. Here's our partial sums. The first was 1/2. The second was 3/4. The third was 7/8. Fourth, 15/16. And what we would like to do is to come up with an expression for the nth one. Well, I think we know what's going to happen in the denominators because they're a geometric sequence and we dealt with those in the previous series of videos. But without rehashing all of that, the denominator is going to be 2 to the nth power. If you played out the geometric sequence protocol that we did, you would end up with that. Because remember, it's the first term times the ratio, which is 2 to the n-1 power. But if you add the exponent, you get 10. What about the numerator? Well, it's just one less than the denominator. So we have a closed form for the nth term, or the nth partial sum, I should say. And so what we would say that the actual sum itself, the sum from 1 to infinity, infinite series, if you will, is going to be the limit as n approaches infinity of the nth partial sum. So it's the limit n approaches infinity of 2 to the n minus 1 over 2 to the n. There's a variety of ways to handle this. You could use L'Hopital's rule if you really wanted to. Hope you remember your derivative rule for 2 to the nth power. Or we could do a little bit of algebraic shenanigans, which would involve splitting that fraction into 2, each with a common denominator of 2 to the nth power. Well, the first fraction would be 2 to the nth over itself, and that's just 1. And then the second fraction would be 1 over 2 to the n, which really doesn't do anything. That back in black, please. Except now we can actually evaluate this limit because this fraction will go to 0 because its numerator is static, it's just 1, and its denominator is approaching infinity. So we end up with 1 minus 0, which of course is 1. So the conclusion that we would draw is that the sum of I equals 1 to infinity of 1/2 to the I power, which means that if we can make this sum get as close to 1 as we want by taking enough terms. We can get that sum within 1/1,000,000th of 1 if we take a long enough partial sum, but it doesn't matter how close to 1 we want to get, we can make that sum get as close as we want by taking enough. Alrighty, so that video went about 12 minutes, which is okay. But we're going to look at another example in the next video that is similar to this one and make a generalization about this geometric series. It's not a geometric sequence, it's a geometric series. Come on, cooperate. I've got stuff jumping all over the screen. It's actually kind of fun.